In the last couple examples, I mentioned the word vertical asymptote. And if you don't quite remember what that is, we're going to recap what that is right now. Okay. And we're going to be able to define it in a little bit more detail than maybe you defined it when you were in pre-calc. Okay. So if the limit as x approaches k, let's say from the right, of f of x, if this is equal to plus or minus infinity, or the limit as x approaches k from the left of f of x is equal to plus or minus infinity, then there is a vertical asymptote at x equals k. Let me highlight the x equals k here. There we go. And let's go ahead and do a couple examples. Okay. So you can see that, say, at x equals -1, that as we start approaching that from the left or from the right, this function is growing without bound. Okay. So is what we can say is that there's an asymptote at x equals -1. Let's write that first. And if we're going to describe the behavior around this asymptote, we would say, well, that the limit as x approaches -1 of f of x is equal to infinity. Now, some of these might require two limits. For instance, this second asymptote at x equals 2, on one side it's increasing without bound, and the other it's decreasing without bound. So we do have another one, but we're going to need two limits to describe it. So there is a vertical asymptote at x equals 2. And to describe the behavior, we have the limit as x approaches 2 on the right of f of x. Okay, coming from the right, we see it's decreasing without bound, so minus infinity there. And if we approach 2 from the left, we see that it's increasing without bound, so this limit is infinite. All right, on to example 4. We're trying to find all the vertical asymptotes and holes. And so we're going to be able to, after this example, figure out how to tell where the holes in the asymptotes are. The first thing that we want to do is factor. If we factor this a little bit, maybe into x plus 2 times x plus 3 all over. And now we're looking for two numbers that add to -2 and multiply to -15. Okay, and then you can see that we can simplify this a little bit. This is x plus 2 over x minus 5. Okay. Now, these two things, they're equal everywhere except for, right, x not equal to 5, and, or, yeah, they're equal everywhere except for when x is 5 and when x is -3. Okay. And they themselves graphically look the same everywhere except for at one of these points, which is at x equals -3. And we're going to talk about that difference though here now. I'm going to break this into two pieces. There we go. So we'll look for the whole here first. And this actually happens at x equals -3. And the way that you're going to be able to tell that there's a hole here is we were able to get rid of all of the x plus 3 factors in the denominator. Right? And is what I mean by get rid of, right, is we canceled out the x plus 3. Okay? And we'll finish this part here in a minute. There's actually one more thing I want to talk about with this, but I want to move over to the vertical asymptote here now. And so you might already be able to guess the vertical asymptote. This is going to happen at x equals 5. Okay. And the way that we can tell this, just by looking at the little bit of algebra we did here, is we were not able to get rid of all of the x plus 5 terms, or x minus 5 terms. Okay, and this one here, we will find the behavior around it here in a second, around this vertical asymptote. But let's jump back to finding the hole here. Okay, we've actually looked at this graphically before in a previous lecture. But again, the idea is graphically, this and this look exactly the same other than at x is equal to -3. Okay. And again, it's because at x equals -3, there's a hole in this one, or in the first one. Okay. And in the second one, there is no hole. Okay. And that's why we're going to be able to actually take the limit of this second one. Let's do that down here. And is what I mean by take its limit is I can take the limit as x approaches -3 of our function f of x, but we're going to use that simplified version of f of x. Okay, and so if we do that, we can use direct substitution with this simplified version. So it looks like -3 plus 2, so that's -1. -3 minus 5, that's -8. And so this is 1/8. And this actually does tell us something. So if you wanted the x and y coordinate of the hole here, we now have the y coordinate. So this occurs at -3, 1/8. Okay, and let's go over to the asymptotes, okay, or asymptote. If we take the limit as x approaches 5, we're going to do that from the right and from the left, just in case those two limits are different. Here we are. And again, I want these both to be of f of x. And I can use the original form of f of x, or I can use that simplified version. Let's make our lives a little bit easier and use that simplified version. So the limit as x approaches 5 from the right of x plus 2 over x minus 5. And same goes for this left-hand limit. Okay. And now let's figure out what these are. So if we were to approach 5 from the left or from the right, the numerator here is going to be approaching 7, right? And in the denominator, since we're coming from the right, we're going to have a small positive. Okay, and so if we have 7 over a small positive, we know that that's going to give us a large positive number. And so the closer we get to 5, the bigger this gets. So this is going to grow without bound, meaning that as we approach 5 from the right, this is going to infinity. And a similar thing is going to happen here. We have approximately 7 on the top, but on the bottom this time, since we're coming from the left, we're going to have a small negative down here. So this is going to be minus infinity.